Thanks. If anybody has the problem sets, I'll take them. Okay, anybody have any questions from last time? Let's just go through what we have left in the semester to do, and then we're getting into a new topic today. We're going to talk about energy methods. Energy methods are mostly a way to approach linkages. That's the main benefit. And so it's kind of an alternative to what we've been doing. I'll try to bring out why it's useful for linkages. So we have an exam next class. So exam 3 is on Tuesday. That would be the 1st. And this is on linkages, the way we've been doing them up until now. I'm sorry, it's not on linkages. It's on the stuff. It's on the stuff that we've been doing up until now, which is particle kinematics in non-inertial coordinate systems. And so to get ready for that, there are a lot of example problems from class. You should know how to do those. There's one practice problem, but it's just sort of more of the same. If you just really understand those example problems and understand the practice problems, you'll be in good shape for the exam. Yep? Oh. Oh, okay, yeah, that's the energy one. Okay, I guess I need to post. So I have practice problems for the for the non-inertial coordinate systems. I need to put it up, I guess. Okay, I'll get that up right away. But you have all the examples from class, so you can work on those in the meantime. But I'll get that up. And then we still have exam 4. That's given during our scheduled finals time. And that, I believe, is Thursday, May, what would that be, the 10th, I think? Yeah. Thanks. 8 o'clock. And that's going to be on the stuff that we're starting today. And we only have 2 lectures to talk about this, so that can't be too involved. I'll put the practice problems up. There'll be example problems from class, and the exam is going to be very similar to those example problems, maybe more similar, than the previous exams because we have so little time to do this. So this is an energy approach to linkages. And then we're also going to have problem set number 3. And that's going to be due by the end of finals week. So due by Friday, May 11th. You can bring in a hard copy to the final or bring it by my office. Or you could also, I'll put a Dropbox in D2L and you can scan it and put it in the Dropbox. Okay, anybody have any questions about what's left in the semester? This isn't too hard because I know this is the only stuff you have to do in your lives right now. So I think it's pretty reasonable. Okay, any questions about, so the stuff for exam 3, particle kinematics in non-inertial coordinate systems. Any questions about that? Yeah.
Example 2, we just stated that the coordinate system is going to be at that rotating spin.
From last class?
I think we went through it.
Okay. Yeah, so I don't want to solve that today because we need to get on to the next stuff. But yeah, let's see. I think I can maybe just sort of set that up. So let's say that we have, so this is the example that is sort of related to the example we did last class, but I said you have to be careful where you put your coordinate system.
My biggest question for
Yeah. So this is the example where you have a plate. And you have a ball on an arm that's hinged like this. And the plate can rotate that way. And the ball can rotate in a circular arc this way. So where do you fix your coordinate system? So what you have to recognize is that the motion of this arm is a simple circular motion if your coordinate system is riding on the plate, okay? If you do anything else with your coordinate system, you don't have, then the motion of this ball isn't a simple circular motion, okay? So that's why you need to recognize that there's two rotations here. One is a passenger on the other rotation. And you want to put your coordinate system fixed to that sort of primary rotation. So the coordinate system, so at this instant, the orientation of the coordinate system, well, I think actually it would make sense to let's put it down here. So we'll put the y-axis there, the x-axis this way, and the z-axis this way. Okay, so now, and the coordinate system is rotating about the y-axis. Okay. So now your r vector. Let's see. Can we just set this up maybe and set this problem up and not go through the solutions? I think that might. Yeah. So you could do it. You could do it either way, but to me, this is the simplest way. Either way, the rotation of the plate needs to be about a vertical line. So if you have the coordinate system oriented, then your omega vector is going to have an x and a y component. Okay, but this way so if this is your body 1, this is your body 2, then omega 1 is just equal to 0, negative 100, 0. And so you're not going to have any acceleration of the origin, right? So in calculating the acceleration of the ball, you're going to have no acceleration of the origin plus the acceleration of the ball relative to the origin. And the acceleration of the ball relative to the origin is going to be your components double dot plus big omega cross position plus 2 big omega dot cross your components dot. Son of a. Thank you. Plus 2 on the exam. Plus big omega cross quantity, big omega cross p. Okay, and then calculating those components dot and components double dot is, going to be a little involved because of where the coordinate system is, but not too bad. Yep. Yeah. Yeah. What if I've been keeping that secret from you the whole time? Okay, so then to calculate your components dot, that's going to be your omega crossed with an R vector. And that R vector, remember, is the vector from the center of rotation to the point of the, that's right, of the arm. So that's not the vector from the origin to the ball. That's the vector from this hinge to the ball. Okay, so this is where you have to make that jump from talking about a position vector to talking about a rigid body rotation about a point, and that R vector is from the center of that rigid body rotation to the point. And then your components double dot are alpha cross R plus omega cross R. Okay. Any questions about that? All right. Anything else about particle kinematics in non-inertial coordinate systems? Okay. So let's get on to, this is an introduction to energy methods for linkages. And this is not going to be on the exam on Tuesday. Oops. Introduction to an energy approach to linkages. And really, it's an approach to any rigid body kinetics, but it's especially useful for linkages. And I'll try to point out why. So we're going to approach energy methods from, like when we talked about, when we used a Newton's laws approach for linkages, our equations of motion were Newton's second law and rotational Newton's second law, right? And then you had to come up with constraint equations. That was always sort of a big part of the method. In this case, our equation of motion is just going to be a single one. So our equation of motion is going to be the work energy principle. Which says that the total work on any system of particles is equal to the kinetic energy of the system of particles at instant 2 minus the kinetic energy of the system at instant 1. And this is true, so this is the work energy principle. And it's true for any system of particles. So it's more general than rigid bodies, more general than linkages. Okay, this is true for millions of particles bouncing around in space or whatever. Okay, but that doesn't mean it's useful for millions of particles bouncing around. Okay, so I'm going to try to point out like what about this makes it especially good for linkages. If you tried to use this for a million particles bouncing around, it wouldn't do you any good. It would be impossible. So it's true for general systems, but it's useful really only for rigid bodies and linkages. Okay, so work energy principle in physics, you dealt with that, right? Work energy principle is the kind of more general statement of what law? Like, you're more used to probably dealing with it as, yeah, exactly. This is the general equation that conservation of mechanical energy comes from. But this one, we have a way to apply external loads. Conservation of mechanical energy is just a totally self-contained thing. Okay, so this is an important distinction. Just because it's true doesn't mean that it helps us at all. So to understand that, so to understand why the work energy principle is useful for rigid bodies and linkages, let's first think about Newton's second law. Okay, so Newton's second law says, wait for my computer. Okay, here we go. Newton's second law says, add up all the forces on a system of particles, and that's equal to the mass times the acceleration of the center of mass of the system, okay? But this wouldn't be very useful in itself, except for the fact that this is equivalent to, so this wouldn't be useful, except that it's equivalent to saying the sum of all the external forces is equal to the mass times the acceleration of the center of mass. Okay, so why can we make this jump with Newton's second law? I mean, that's a key jump, right? Like if you're talking about 1 million particles bouncing around, this is what lets you ignore all the internal forces from the particles bouncing against each other and only worry about the stuff happening to, say, one particle over here on the side, you know? So why are these equivalent? You know what I'm asking? Have you thought about that before? Like, why is Newton's second law just, why do we only deal with the external forces? We never have to add up all the forces of one part of a metal bar acting on the other part of a metal bar. That's true. I mean, that's what these being equivalent says, and the reason that it's true is because of Newton's third law. You know, so this is true. This equivalence is true because Newton's third law says any force F12, you know, say there are two internal to your system, you have a body 1 and a body 2. There's a force vector F12. There's also a force vector F21. Those are equal and opposite. And so if you add those up, they add up to 0, and so they cancel out, you know? And so that's why you can cancel out everything except the external forces. Okay, so let's think about that with work, because with the work energy principle, we're talking about work on systems. So with work, that doesn't happen automatically. Let's say the work done by internal loads doesn't automatically cancel, doesn't always cancel. And to see that, think about, you know, the definition of an increment in work. some little quantity of work. I don't know why my computer's been so slow. So an increment of work dW is equal to the force vector dotted with an incremental change in the position. Okay. And there's no guarantee. How do you spell guarantee? UA or AU? No guarantee that the increment in the incremental change in position of the two particles is going to be equal and opposite. Okay. Or actually, so there's no guarantee that this incremental change in position is going to be the same. So even though F12 has to be equal and opposite to F21, okay, if you have this F12 times some increment of position change, and you have the negative F12 dotted with some totally random change in position, those two work quantities aren't going to add up to zero. Okay, you see what I'm saying? So there's something different about the canceling of internal works and the canceling of internal forces. Okay, internal forces always cancel. Internal works, they don't always cancel, and we're going to have to think about the cases when they do. Any questions about that? Okay. Yep. They don't always cancel just generally, and I'll draw a picture of why when it doesn't. So when does the work due to internal forces cancel? Well, if you have two particles that are stuck together, that move together, okay, so say there's your particle 1, here's your particle 2, they're stuck together. So they have a shared velocity vector like that. Draw a free body diagram, particle 1. And there's a force vector, F12, whatever direction that force is. Your free body diagram of particle 2 has an F21, which is equal to negative F12. So the increment in work on particle 1 is equal to F dotted with some incremental change in position, right? The increment of work done on particle 2 by this internal collision, this F is F12, right? This is equal to negative F12 dotted with that same incremental change in position. Okay, so the total work, total increment in work, you add these two up and you get 0. Okay, that's when they do cancel. So these two particles being connected to each other, moving together, is like a key thing for being able to cancel out works due to internal forces. Okay. When wouldn't it cancel? So let's think of a case where they're not moving together. So when do the works due to internal forces not cancel? So say you have two particles that apply this force to each other, but this one's going this way, and this one's going this way. Okay. The free body diagrams, of course, but from Newton's third law, still say that these forces are equal and opposite, right? Body 1 has the force F12. Body 2 has the force F21, which is equal to negative F12. But now the increment of work for body 1 is F12 dotted with some dP1. And the increment of work for body 2 is equal to negative F12 dotted with some increment dP2, right? There's no reason, these are in different directions, so these aren't going to cancel, right? So your total increment in work is d work 1 plus d work 2, and that's not equal to 0. Okay. So this isn't going to be very good at dealing with cases. This energy method isn't going to be very useful for dealing with cases where particles move independently. But this makes it look sort of natural for dealing with collections of particles that are organized in some way, like rigid bodies, okay? The internal loads from one piece of metal to the next piece of metal for a rigid body, they do move together, okay? They're stuck together in this rigid body. So we're going to be able to ignore certain kinds of internal loads when we calculate the work, okay? Yep. Well, the dot product, the dot product has the direction affects the dot product. So no matter what the magnitude is, you're going to get different dot products out of those, and they're not going to cancel. Okay, so this suggests that the energy approach will be more useful for systems where particles move together. What are some examples? Well, rigid bodies. And another example is pin joints between rigid bodies. Okay, so even though there's a rotation at pin joints, the force is applied at those pins. The particles have to move together, right? They're fixed together, and so pin joints are going to be easy to deal with. We're not going to have to worry about work due to internal forces at pin joints. Okay, and that makes you think, I might try this with linkages. That might be a good way to go. If that doesn't occur to you, I can't help you. Okay, so what about external loads? And this is a really nice benefit of using an energy method. So what do you do? So what we just talked about was some of the times that come up a lot in linkages where you can avoid calculating the work due to internal loads, right? What about the external loads? When we're dealing with Newton's laws, we always have to deal with every external load, right? But we're going to see that with energy methods, there are some times that those will be zero too. Okay. So several types of external loads do zero work too. So first of all, based on that definition of an increment of work, it's equal to a force times an increment in change in position. So first, if a particle doesn't move, no matter what the load is, there's no work done, right? And so we always put all this energy into calculating loads that we might not necessarily want at like fixed pin joints, just because we need it to complete the set of equations. In this case, like at a pin joint where something doesn't move at all, no work is done, and so we can ignore that. We never have to even deal with that force, and that's a nice benefit. So if the particle where an external force is applied doesn't move, then dP is a zero vector, and so there's no work done. Okay. So let's say you can ignore reaction forces at pin joints that are connected to the ground. Okay, that's a big deal. That helps a lot. The second type of external load that does zero work is when, so based on that dot product definition, when is the dot product of two vectors equal to zero? If one of the vectors is zero, of course it is. When else? If the two vectors are perpendicular, then the dot product is zero. Okay, so if the path of particle motion is perpendicular to the external force direction, then the work is equal to this dot product, and it's equal to zero. Okay, so this isn't going to be quite as useful as the first one, but this is going to come up a lot. Okay, so this is very useful. And so here are some examples where those come up. If your linkage has rollers, wheels, sliders, pins moving in slots. In all those cases, the reaction force is perpendicular to the allowable motion, okay? And so the reaction force for all of these kind of joints, if these are connected to the ground, okay? In all these cases, there's zero work done by that reaction force, okay? Also, any kind of normal force, a normal force from the ground does zero work. And also, the last one is any kind of centripetal force during a circular motion. Okay, so the object in this case is moving in a circular path like this, if that's the particle. If there's a force applied that way, its instantaneous direction of motion is this way, right? And so those are perpendicular, and so zero work is done by a centripetal force. Okay. So again, notice you see a benefit for linkages. This is all of these times that you can throw away the work, not worry about it, are useful things that come up all the time in linkages. And that's why we're going in this direction for linkages. Okay. Okay, so now what we have to do, that was just sort of a motivation for, like, what's the point of, why are we only going to do this for linkages? Why not for collisions or whatever? It's not that great for collisions, but it's good for collections of rigid bodies connected by joints, okay? So now we're going to focus on how to do these calculations, okay? So now we're going to focus on rigid bodies and linkages. And the question now is just, how do we compute, first, the total kinetic energy for a rigid body and a linkage? And second, how do we compute the total work? And we're going to break this up into two calculations. The work due to a force and the work due to a couple. Okay, so I'm going to go back to, the first thing I'm going to do is talk about how to calculate the kinetic energy. We'll do some example problems. Then we'll talk about how to calculate the work due to external loads. We'll do some example problems, and then we'll put it all together. And we'll see that there's going to be one more thing that we need. Okay, like, we're going to see that the total kinetic energy and the total work is going to involve a bunch of variables, right? We're going to have omegas for all the different bodies. We're going to have F's for all the external loads. These are all variables we're going to have to solve for. And we only have one equation of motion. So if we have more than one variable that we're dealing with, and that's pretty much always going to be the case, we're going to have to come up with geometric constraints. We're going to have to come up with constraint equations until we have as many equations as we have variables. Okay, so the third thing we're going to have to deal with, and it ends up usually in these kind of problems being the most complicated part, is the constraints. Yep, exactly. Although I don't condone that kind of language. Okay, so let's talk about how you calculate the kinetic energy of a rigid body. Anybody have any questions yet? Questions about the sort of motivation for this? Okay, so we have three kinds of calculations we're going to have to deal with. Kinetic energy, work, and constraints. So kinetic energy of a rigid body. Did you do this in physics? Okay. So remember when we were talking about Newton's laws, rotational Newton's law, we dealt with things separately in the case, like if a rigid body had a fixed point, we dealt with it one way. If it didn't have a fixed point, we dealt with it a different way. We had a different about point. And we're going to make the exact same distinction here, and it's going to be an analogous treatment. Okay, so if an object has a fixed point, to calculate kinetic energy, we're going to do everything about that fixed point. If it doesn't have a fixed point, we're going to do everything about the center of mass. Okay. So think of this as related to rotational Newton's second law. We're going to break this into two cases. The first case says, okay, and I guess let's number this 1 to match the 1 up ahead, up above. So this number 1 is everything that we're going to talk about, kinetic energy of rigid bodies. Then we'll move on to number 2 and talk about work. So the two cases here are A, if the object, the rigid body, rotates about a fixed point, and the second case is it doesn't have a fixed point. So for case A, the rigid body rotates about a fixed point, like a pin joint, connected to the ground, right? Then the total kinetic energy of the body is 1/2 times the moment of inertia about the fixed point times omega squared. In the second case, if the rigid body has no fixed point, then the kinetic energy of the object is equal to 1/2 times the moment of inertia about the center of mass times the body's angular velocity squared plus 1/2 times the object's mass times the velocity of the center of mass squared. If you have the velocity as a vector, you can also calculate that as 1/2 times the mass times velocity of the center of mass dotted with itself. And remember that with Rn2L, the case of no fixed point, that actually is always true. Remember that? We didn't use it when we had a fixed point because it's simpler to use the fixed point, but you always could go this way, and that's true here too. So this is actually always true. It's just that there's a benefit to using this method if you do have a fixed point. Okay. Okay, so let me do an example. So let's say that a ball rolls down an incline without slipping, and say that its instantaneous speed is 3 meters per second. And say that the ball's radius is 0.1 meters and its mass is 0.5 kilograms. What's its kinetic energy? So first I'm just going to do it defining two variables, okay? So first, we'll just think of it as like, we'll start by treating omega and the speed as independent. Okay. But you know that they're not independent if it's rolling without slipping, right? So then at that point, you can deal with the constraint equation, right? But we can start by just saying, okay, it's going to have a speed, it's going to have an angular velocity. We can deal with both of those, worry about the constraint equation later. And that's kind of the way I would always recommend approaching these. So in this case, is there a fixed point or not? It's rolling freely, right? So no fixed point. So the kinetic energy is equal to 1/2 times the moment of inertia of the ball about its center of mass times omega squared plus 1/2 times the mass times the speed of the center of mass squared. The moment of inertia of a sphere, that's just a formula you can look up. So you get 1/2 times, this formula is 2/5 times 0.5, the mass, times the radius squared, times omega squared. And then plus, this term is 1/2 times 0.5. And we know that the speed is 3 meters per second. Okay. So, it looks like this whole, if you multiply all this out, it looks like that gives you 0.001, I think. Omega squared plus what do we have here? 0.25 what's 0.25 times 9? What? 9/4. Okay. Okay. So no. Can someone just plug that in? Okay. Okay. So that's the kinetic energy, but we know that that omega is constrained by the speed, right? So now we have to deal with the constraint equation that relates our different variables. Okay. So the constraint equation says, so this is rolling without slipping. You talked about this once briefly. We haven't done any rolling in this class, but I mean, we rolled down that hill that one day. That was awesome. But we haven't calculated any rolling. So the speed of the center of mass is equal to the radius times omega. So 3 is equal to 0.1 omega. So omega is equal to 30. So that's our constraint equation. And so then our kinetic energy is 0.001 times 30 plus 2.25. And so I think you get a value of 3.15. All these units were SI units. Yes. I think if you do this, you get 3.15. Everything was SI units. So what's the units of kinetic energy? Joules, yeah. Any questions about that? Okay. So here's an example I'd like you to do and compare your answers to each other. So say that we have a rigid body that's fixed to the ground by a pin. We'll call it a slender rod with a length of 1 meter, a mass of 5 kilograms, and let's say that it has an angular velocity this direction of 10 radians per second. And the question is, what's the kinetic energy? So this rotates about a fixed point at the pin. So the moment of inertia about the center of mass. So our about point is going to be the pin. So for a slender rod, the moment of inertia about the center of mass is 1/12 times the mass times the length squared. And so the moment of inertia about the pin is 5/12, that's 0.4167, plus parallel axis theorem says 5 times, what's the distance here? 0.5, so 0.5 squared. And so you get 1.667 kilogram meters squared. So then the total kinetic energy is 1/2 times 1.667 times omega squared. And so you get 83.33 joules. Okay. Any questions about that? So this one, you could also do the other way, right? The using the center of mass as your about point always works. It just isn't as simple when you have a fixed point. So you could do this the other way. You could do it with the about point at the center of mass. You would get the moment of inertia about the center of mass is 0.4167 kilogram meters squared. The rotational kinetic energy, so the total kinetic energy we can think of as the rotational kinetic energy plus the translational kinetic energy. Okay, this rotational, so this is the one that's 1/2 I omega squared. This is the one that's 1/2 mv squared. For the rotational, we have 1/2 times 0.4167 times 10 squared, so 20.833. For the translational, we have 1/2 times the mass times VCOM squared. And so the total kinetic energy is 20.833 plus 2.5 V center of mass squared. Okay, and now, so I did this, left all the variables in, and now we'll think about how the constraint works. So the constraint we can use here is that the velocity vector of the center of mass is equal to omega crossed with r, right? I guess I didn't give an angle, but this omega is going to be 0, 0, 10. that R vector, we could think of it as being straight up, okay? And that you'd have 0, 0.50. That's right, because we're trying to find the velocity of the center of mass. So you're going from the fixed point of the rotation just to the point you want, okay? So what you would get here is a velocity vector of negative 5, 0, 0, right? So dot these, and you get 25 meters per second, right? And so plug that into T total, and you get 20.833 plus 2.5 times 25, and you get the same thing. And that's good. Yep. Yeah, so it turns out, right, if you do it in terms of just speeds, then the position it's at doesn't matter. But since I started doing it like a vector, I needed to know what position it was in. So I kind of just glossed over that. One way you could do it is, so really to do it generally, you'd set it up with a cosine and a sine in your vector, in your R vector, and you'd see, that cosine squared plus sine squared equals 1, so the angles would cancel out, they wouldn't matter. Okay, can you picture what I mean? And yeah.
So is this the amount of energy that it takes to move this rod at this speed?
No. Well, the reason we want to find this is because we're going to use it in the work energy principle. Okay.
So it's just a means of solving.
Right.
Like getting the same answer.
Well, the answers are going to be in a little bit of a different form. So, like, remember when you talked about mechanical energy of particles, in physics? You could do the same kind of problems using Newton's laws that you could using energy methods, right? But what you get is a little bit different. Like when you solve Newton's methods, you get accelerations at an instant, right? When you solve using energy methods, you get speeds as functions of an amount of motion that you've gone through. You remember, you know what I'm talking about? Like, for example, think of the example of a guy sliding down a hill with no friction, skiing down a hill, okay? If you're doing a similar problem, so you're trying to figure out like how fast this guy's going. At the bottom of the hill, How would you approach this using Newton's laws? At every instant, you'd figure out the direction of the normal force, right? You'd use Newton's second law to calculate the acceleration. You'd come up with an acceleration as a function of time. And if you're trying to find the speed at the bottom of the hill, you'd have to integrate this function of acceleration through that whole motion. Okay? So you can do it that way, but it's a nuisance, With energy methods, it's really easy. You just recognize that there's no work done by the normal force because the force is perpendicular to the motion at every instant. And you use conservation of energy, and immediately it just gives you the speed at the bottom. Okay, so you can solve that problem both ways, but some problems, what you're looking for is a lot simpler with an energy method. Sometimes it's a lot simpler with Newton's laws. So yeah, we're doing the same problems we did before, but we're going to get it in a different form. And depending on which form you want, one way is more useful or the other way is more useful.
So do we need the same amount of criteria for both methods, or do we do?
Yes. Yep. Yeah, it doesn't reduce the amount of information you need to make it solvable. It just makes the math easier or harder. I'm getting this out of here. Okay, I want to do one more example. I want you to do one more example. We don't really have time right now, but I'm going to write it up here. You can look at it, ask questions if you want to. If you have time before, yeah, the test is Tuesday, so I assume you're not going to think about this too much before the test. But if you have time before class on Thursday, spend a minute thinking about how to approach this, and we'll do this example problem in class. So now, instead of just a single rigid body, say that we have a linkage. Okay. So say you have a roller over here. A pin over here. Let's call this body 1. Body 2. And let's say that the angular velocity of body 1 is 5 radians per second. And the masses of each body are 10 kilograms. The length of each member is 1 meter. And the question is, what's the total kinetic energy of the linkage? And the reason that we do this is, like we were just saying, to calculate the stuff on the right side of the work energy principle. Any questions about that? So what about omega 2? Did I need to give that to you? No, because you can figure that out from a constraint equation. The same way you had to in the problem set. It's sort of a simpler version of that. Okay. Yep. Yeah, that's what I had in mind. So at least with me, you can assume that. Any other questions? Okay. I have office hours Monday from 4 to 6 if you want to ask any questions before the exam. And if you can't make it to those, feel free to email and set up an appointment. Okay. See ya.